So now we understand that there's a difference between working an equilibrium problem in terms of moles and working that same problem in terms of molecules. So the equilibrium constant expressed in terms of moles, the equilibrium constant expressed in terms of molecules, which we can just call K, or if we want to, we can call K sub capital N. Those are related to each other by Avogadro's number raised to the power 1 over Avogadro's number raised to the power delta nu, where delta nu is the change in the number of molecules as I go from reactants to products. That will also have some important consequences when we think about equilibrium constants expressed in terms of pressures, which is often a convenient way to work the problem. So in the examples we've seen so far, the HBr example and the BR2 example, all of the reactants and products are gases, have been gases. So if we're working an equilibrium problem using gases, and if we assume that those gases are ideal, then the equilibrium constant, which is the product of molecules raised to stoichiometric coefficients, the number of molecules of a gas is just PV over RT or PV over KT if the gas is ideal. So if I rewrite number of molecules as PV over KT raised to the stoichiometric coefficient, this is another way of writing the equilibrium constant. The only one of these four terms that depends on the species is the partial pressure. The pressure of each gas may be different, but they're all occupying the same volume, they're all at the same temperature, and Boltzmann's constant is always the same. So if I take those V over KT terms and I move them outside of the product, I get V over KT raised to a bunch of stoichiometric coefficients multiplied by the product of all the partial pressures raised to their stoichiometric coefficients. So again, the sum of the stoichiometric coefficients is this thing we're calling delta nu, the change in total moles of species during the reaction. And then what I have left at the end here, this product, not a product of molecules raised to stoichiometric coefficients, but a product of pressures raised to stoichiometric coefficients. So I can define that thing, so that product, I define that and call that K sub P. It looks like an equilibrium constant, but using pressures instead of molecules. So we call that K sub P. And what we've discovered is that the equilibrium constant written in terms of molecules is related to the equilibrium constant in terms of pressures by this factor V over KT or V over RT raised to the delta nu. And you can think of this V over KT to the delta nu as essentially just a unit conversion that will allow us to convert units of pressures to units of moles, just like we did here using the ideal gas expression. So to make sure that idea is clear, we can work an example. Let's again repeat this BR2 example where I've got two bromine molecules forming two bromine atoms forming a bromine 2 molecule. So just to make sure it's clear, the change in number of molecules, which is the sum of the stoichiometric coefficients. I've got a -2 when I consume two reactant bromine atoms and a +1 when I produce one Br2 molecule. The sum of those stoichiometric coefficients is -1, again meaning I lose one molecule every time the reaction goes. I turn two molecules into one. We know from previous work with this example that the equilibrium constant depends on volume. We've determined that it's this number 1.6 times 10 to the 7th liters times 1 over the volume that the gas is contained in, and that's the value when I'm doing the problem at 298 Kelvin. So if we want to know what the value of Kp is, using that expression we've just determined, we know K, we want to know Kp. So if I rearrange this expression, Kp is equal to Kt over V raised to the delta nu times the value of K that we already know. In this case, delta nu is -1, so that if I raise Kt over V to the -1, that turns into a V over Kt. The K value that we know is 1.6 times 10 to the 7th liters times 1 over V, and now look what's happened. The V in the conversion cancels the V dependence of the equilibrium constant, and it turns out that Kp, I can plug in these known values of the equilibrium constant and K and T. Turns out now that Kp does not depend on volume. The value of Kp, the equilibrium constant expressed in pressures, is just this value regardless of what volume I'm doing the reaction in. So it's this value in a 1 liter box or a 10 liter box or a 50 meters cubed box, which is one reason it's very convenient to work with Kp rather than the equilibrium constant written in terms of moles. So to see how that works, we can repeat the numerical example we've done before. Let's say we have put 1 mole of bromine gas into a box with volume 1 liter at 298 Kelvin. But we want to work this pressure not in terms of molecules, not in terms of moles, but in terms of pressures. So the initial pressure of the Br2 gas is moles times RT over V. So if I use the right value of R and T and V, and I'm careful with units, that works out to be a pressure. That should be a pressure, not a volume. A pressure of 24.5 atmospheres for 1 mole at 298 Kelvin in a 1 liter box. The question is, what's going to happen to that system once it reaches equilibrium? Once those Br2 molecules dissociate partly and form bromine atoms in this 1 liter box, how many bromine atoms are we going to form, or what's the pressure of the bromine gas, the bromine atoms that we're going to form? So what we know is the pressure of Br2 and Br is, because they're ideal gases, that's going to be moles times RT over V for each species, moles of Br2, moles of Br. At equilibrium, we know that moles of Br2 is however many we started with plus the extent of reaction, because the products are produced when the reaction goes, and it's the amount we started with, 0 Br, minus twice the extent of reaction, because 2 moles of bromine are consumed every time the reaction goes 1 mole of times. If I rearrange the top expression, N naught plus squiggle times RT over V, I get N naught RT over V plus squiggle RT over V. This last term, I can think of this as the extent of reaction converted into units of pressure, right? So instead of writing down squiggle RT over V a bunch of times, every time I see squiggle RT over V, I'm going to just write down lambda. So I've defined a new variable lambda, which is equal to squiggle RT over V, and I'm going to think of that as the extent of reaction expressed in units of pressure. And likewise, N naught RT over V, that's just the pressure of the initial pressure, P naught, of the Br2 gas. Same thing if I rewrite squiggle RT over V as lambda in the second expression, then the total pressure of bromine is going to be minus twice lambda, minus twice the extent of the reaction written as a pressure. So now I have enough information to plug into my equilibrium expression. Kp is some value that I know. That's the equilibrium constant written in terms of pressure, so it's pressure of the products divided by pressure of the reactants raised to the appropriate powers. I've just figured out that the pressure of Br2 is initial pressure plus lambda. Pressure of bromine atoms is minus 2 lambda, so when I square that, that becomes 4 lambda squared. Again, I have a quadratic equation to solve when I rearrange this. When I solve that quadratic equation, the value of lambda numerically, I get 2 values, but the one that's physically meaningful works out to be -4 times 10 to the minus 15th, and it comes out in units of atmospheres because Kp had units of 1 over atmospheres. So what does that mean for our total pressures? Total pressure of Br2 was the 1 atmosphere I started with plus squiggle, so plus this negative amount. I've consumed an amount of Br2 equivalent to that many atmospheres. So again, that number is small compared to the initial amount. I've dissociated a negligible amount of the Br2, and I still have a pressure of 1 atmosphere worth of Br2. For bromine atoms, I have -2 times squiggle, or -2 times this negative number, which gives me about 8 times 10 to the minus 15 atmospheres worth of bromine atoms. So again, I've dissociated a little bit of Br2 to form enough Br to make the pressure 7.9 times 10 to the minus 15 atmospheres. And notice if I divide that by the total pressure, the 24.5 atmospheres I started with, that's 3.2 times 10 to the minus 16th of my initial pressure. So if you think back to a previous lecture, that's exactly the same result we got when we worked the problem in terms of molecules. So we get the same answer when working the problem in molecules as we do when working the problem in pressures. It's a little more convenient, perhaps, to work in terms of pressures than molecules. It's certainly more convenient when we remember that we're able to use this value of Kp regardless of what the box size is. So no matter what box size I'm working in, I can use the same value of Kp. So that's another advantage of doing the equilibrium problem in terms of pressures.